We have also the Klein-Gordon equation. And then later on we'll do the Maxwell vector potential. Okay, but I'll show you the most conceptually novel and sort of more difficult one is the Dirac equation, because there are 4 components and these funny matrices, so that part takes some getting used to. Okay. So in fact, let's begin with the Klein-Gordon equation. I think we did a little bit of it, but let's just recap what's going on. So I'm going to define something called E, and what we find is that each Fourier mode is easiest to do in Fourier space, and each Fourier mode must begin there. So look at one Fourier mode. Okay, and so what you discover is that maybe I'll put it this way. This is P naught, and then if you look at one Fourier mode, you will discover that, let me put it as I P mu x mu, and if you apply the Klein-Gordon wave operator on this plane wave, you discover the following, right? That each derivative is essentially minus I P mu. There is correspondence between them in the sense that if you add a derivative on the plane wave, you get this. And if you're in Fourier space, every time you see this, you can think of it as the derivative acting on the plane wave. So it's equivalent essentially because of this because of the fact that this guy is a basis function, right? So then what you discover is this guy is nothing but P squared, where P squared here means P alpha, right? And the partial derivative will give you a minus I squared. So this would be minus plus m squared e to the I P dot x. But this is supposed to be 0 since, like I said, this is a basis function and you're trying to construct the most general solution. So what it's telling you is that this dispersion relation must hold. That P squared is m squared, and P, and which tells you that, which tells you this basically. So I should really call P0 plus or minus square root, but I prefer to call it energy. Right? So energy will turn out to be either plus or minus P0, which is either plus or minus square root of P vector squared plus m squared. And so what you discover is that, of course, if you have a minus I P0 x, you also could have so equally valid solution is, of course, just e to the plus I P dot x. Right? This is the notation why I use P naught with this definition. And this you should think of as basically the negative energy solution, right? So it's minus I, but minus square root P plus I K dot x. That's basically what's happening. Whereas this guy, e to the minus I P dot x, is, you should think of it as the positive energy solution plus I K dot x. I'm sorry, minus. There's a sign difference because of the following, right? P0 T, P mu x mu is P0 x0, which is P0 T, plus Pi xi But if you want to write it as a dot product, this will become P0T minus P vector PIXI, and this guy is P dot X. For this case, I want to be a bit more careful about the sign, upstairs to downstairs. Okay, so these are the two possible solutions. And in fact, what you discover is that, of course, this is nothing but a complex conjugate of this, and vice versa. So the most general 5x should just be the sum over all of these basis functions. And so, because p is continuous, we write it as a Fourier integral. Okay? And for convenience, so I'm going to have arbitrary coefficients multiplied to this, and arbitrary coefficients multiplied to this, and it's going to be summed over all possible coefficients, right? So what I'm going to do is I'm going to call it basically phi tilde. Actually, let me do the formula. Let me just call it A tilde, or maybe alpha tilde of P, right? So it can depend on P. And what I'm going to do is I'm going to divide it by 1 over 2 P naught, square root of 2 P naught. So this is just, because this is arbitrary for now, this is just a rescaling, which I'm not losing anything by doing that. Right, so this will be I P dot X, and then I'll have alpha star P over square root 2 P naught, and then e to the minus I P dot X. Okay, remember this is real. For now, this is real. So you see that once I write this down, I don't have a choice. I need to have this complex conjugate. Right? So in some sense, once I have one of these solutions, I will get the other one. I don't really have a choice because it's a real scalar field. So I need both of them. And let me just mention that the reason why I rescale it like that is completely arbitrary. But later on, we're going to quantize this field, and it will be this alpha and alpha star that becomes quantum operators, become linear operators, and this is going to be the place where we make the contact between the fields and the particles, but one step at a time. Okay, so that's the Klein-Gordon part. So the next step is to do Dirac. Okay. So how does Dirac look like? So again, we discovered that our positive and negative energy solutions. Let's just write it down first. P, U of P, the positive energy solutions. I'm using basically Pascal's notation because the positive energy solution is U. And then the negative energy solutions he calls V. But what is it? Is one is the first, in the wild basis, the left-handed guy will be square root of P dot sigma times an arbitrary spinner. This is a two-component guy. And let me just mention, this guy should, of course, can depend on P as well. And the arbitrariness of this is like the arbitrariness of these coefficients. Okay? So whatever superposition coefficients that show up when we get the most general Dirac solution, that's the analog here. This guy over here, as well as the alphas over here. That's the analog. And then you have P dot sigma bar, and then the same C. Okay, the same C that needs to show up here. And then e to the minus I P dot X, where P0 here is always the same, it's always the same definition. Okay? And then for the negative solution, negative energy solution, what you have is V of P times e to the plus I P dot X is now equals to, again, the left-handed while spinner will be P dot sigma, and then it will be C prime. I call it prime because in principle, these spinners can be different from them. And then we have P dot sigma bar with a minus sign here, C prime, e to the plus I P dot X. Okay. So I have a few things to explain. What is the square root? And then secondly, how do I know it's a solution? Let's check it. Let's check that this is in fact a solution. So the square root of an operator, of course, is a little bit ambiguous because square root itself is a multi-valued function. So I better make sure I properly define what I mean by square root, right? So in fact, if I take the square root of a number in this situation, this is the positive square root. So what it means is the following. Remember that P dot sigma is P mu sigma mu, which in turn is P0 identity, right? Because sigma 0, remember we define it to be the 2 by 2 identity plus I, Pi sigma I. Okay, so these are the usual Pauli matrices, but I've extended it to the 4 to include the 0 component, because then sigma mu becomes the complete basis for 2 by 2 matrices. But if you remember, or rather you don't have to remember, you can just observe, this is an identity, and this definitely commutes with sigma I. So once you know how to diagonalize this guy, remember this is in fact our helicity operator. Particularly if you divide by 2, then it will just be the spin half projected along the momentum. That's exactly what helicity means. So, in fact, you will, I'm forgetting now, I think this is one of your homework problems, but P hat I, sigma I, can be diagonalized. I put a hat just to say that this is Pi divided by the length of P. Now, that is saying that I just care about the direction, but not the length, right? But I can always stick it in back later. The point here is that there are only 2 eigenvalues because sigma I is a 2 by 2 matrix, and one is plus and one is minus. Remember that a permission operator can always be written in the diagonal basis in terms of its eigenstates, right? Remember this is a very general statement. So in this case, for my P hat sigma I, the 2 eigenvalues are plus or minus 1. So plus 1, minus 1, and these guys are just my while spinners, right? A plus sigma B dot plus star, and then C minus A, and then C minus B dot star. Right? Again, these are the eigenvalues. These are the eigenstates where they correspond to these guys. But because there's a complex conjugate here, and we have just discovered that complex conjugated spinors transform in an inequivalent way from uncomplex conjugated spinors because of the boost part of the Lorentz group. Right? But anyway, so this is what it should look like. And therefore, once you write down P I sigma I, all you have to do is just multiply throughout by the length of the momentum, which now just gives you C plus A, C plus B dot, complex conjugate, minus C minus A, C minus B dot, complex conjugate. Okay? And then P0 sigma 0, well, what is that? P0 sigma 0 is just P0, which is the square root, times the identity. But remember that for a Hermitian operator, its orthonormal eigenstates can be used to span the space that you're in, which means that the identity operator itself, you must be able to write it in terms of the orthonormal basis. Just a basic fact about linear algebra. I should probably mention that I normalize them to 1. This is 1 plus minus, and then if you dot them, I'm sorry, I need a dagger. If you dot the plus into the minus, you discover they're orthogonal. And this, remember, is just a consequence of the fact that they are eigenstates corresponding to different eigenvalues of a Hermitian operator. And it's a theorem of linear algebra, right, that eigenstates of different eigenvalues must necessarily be orthogonal. So altogether, you can combine them and write down what is P mu sigma mu. Yeah, that's the first step. So P mu, again, P mu sigma mu, we discover, can now be combined as this eigenvalue plus this eigenvalue multiplied by the same complete eigenbrackets, right? So P0 is just, remember, the square root, positive square root. So this, for us, will always be greater or equal to 0. And so this will be P0 plus P magnitude times C plus A, C plus B dot. And then P0 minus P times C minus A, C minus B dot, complex conjugate. So if I do P mu sigma bar mu instead, what it means is I just flip the sign of the spatial components, right? So this is P0, sigma 0, and then sigma bar, remember, is actually just the sigma mu's, but with the spatial components sign flip. Right? So this is minus pi sigma I, which means that if I try to diagonalize it, then all I need to do is just stick in a minus sign over here, which means in front of the plus, I now have a minus, and in front of the minus, I now have a plus, which just means that this guy is just now P0 minus length of P, C plus, and then P0 plus length of P, C plus. Oops, I'm sorry, minus. Yeah. If I make a boo-boo, you must catch it faster than I do. Okay? You guys are still young. Okay. Okay, so now square root is easy to define with this, now that we know how to diagonalize these guys. So what does square root mean? When you take the square root of an operator, what it means, and if it's permission, then this just means that I take the square root of its eigenvalues, but then I just sum it over the same states, right? So this is basically like this guy, except that I literally take the square root of all its diagonal components, which is the eigenvalues. Of course, like I mentioned, the square root itself is ambiguous, right? It's a multi-valued, or rather a double-valued function. But for us, we are going to use that definition where square root is the positive square root. So if you like, it's a definition. But for sure, you can check that when you take an operator like that and you square it, okay, then because these guys are orthonormal, you will find that this is nothing but lambda. Okay, should be, if you're familiar with the linear algebra, this should be immediately obvious, and this is in fact A. Okay, so we have cooked up an operator that solves this equation. What is the object squared that gives you back the original guy, right? And that's the solution. And likewise, we can use a similar definition, which is square root. I should say, we're doing all this because we just want to use this as a tool to write down the solution to the Dirac equation, right, in a useful form. So part of it is definition. This is definition, but the construction we'll see right, very soon is very useful for verifying that what I've written down over here just now, which unfortunately I've erased, is in fact the solution. So if you follow this, then what I do is I come to P0 plus P, and this is now square root of P0 plus P. Okay, so let me just, let me just write it down. P, and then C plus, and then square root of P0 minus P, C minus. Okay? And then likewise, if you have the P dot sigma mu, P dot sigma bar, it's basically almost the same, except now I flip the sign of the magnitude of P. And remember, that's because you're basically sticking a minus sign in front of sigma I. Okay, so this will be P0 minus P vector, and then C plus A, C plus B dot start plus P0 plus P, and then C minus A, C minus B dot start. Okay, so with this definition, let's now come and observe why this is useful. Okay, one of the key reasons why it's useful is now you know how to multiply these guys. If I multiply P dot sigma with P dot sigma bar, let's see what happens. Well, they are both diagonal in this basis, right? So you can see right away that because they're both diagonal in this basis, this is like lambda bra, lambda cat, lambda bra. It's the same lambda cat, lambda bra, right? So they're diagonal in this basis. So when I multiply them, I'm basically just multiplying their eigenvalues. And that also tells you that as far as they are concerned, they commute. Right? In other words, they're simultaneously diagonalizable. Okay, so again, this is a matrix, that's also a matrix, but because they're diagonal in the same basis, you can just multiply them in any order you want. But let's see what you get here, right? So when you multiply them, you get that this is just nothing but square root. Remember, it's a positive square root, so I can just take the square root and multiply them together. And what you discover is that this is alpha plus beta, alpha minus beta, so you get p squared. The Lorentz version of p squared, right? Meaning p alpha times c plus a b dot plus p squared, and then c minus. Okay, and now this is a common factor, and remember this guy plus this guy is nothing but the completeness relation. We have it somewhere. It's this guy over here. So just nothing but the completeness relation. Okay, and this is just now the identity. And p squared is what? Well, p squared is exactly the dispersion relation, which we erased. But p squared, remember, is exactly p0 squared minus p vector squared. In my sign convention, is p0 naught, p naught squared minus p vector squared. And this is, of course, nothing but the mass squared. Right. This is just Einstein's famous formula. But now you can see it, this dispersion. Now you see where it comes from a field theoretic perspective. Okay. In other words, this is just n times the identity. So now we're in business. We can now verify that, in fact, what I wrote down earlier is a solution. Are solutions. Any questions so far?
Is a square root of operator also well defined when the eigenvalue lambda is negative?
Yeah, sure, you can define it. But again, remember when you take a square root, there's always two solutions, right? And so you got to be careful what you mean by that. But otherwise, if you define it whatever you want, as long as it's consistent, then it's of course completely okay.
But when A is Hermitian and the eigenvalue is negative, when we square root, the eigenvalue is complex, and
it's okay. It's okay.
In the longer Hermitian.
Yeah. Remember that square root of an operator just means that, what does it mean? It means all you have to make sure is that when you multiply them together, you get back A. Right? This is the definition of the square root of an operator. Right? It's just you just have to cook up a solution so that when you multiply it to itself, you get back the original operator. That's what square root means. But because of that, there are always, for square root, there are always